Welcome to Module 3, Chapter 10, on Advanced Systems Thinking for Sustainability Transitions. In this chapter, we embark on a journey to understand how our actions today shape the world of tomorrow. Sustainability is the practice of meeting our current needs while ensuring that resources and ecosystem health are preserved for future generations. This concept is not just about environmental protection, it's about balancing economic growth, social equity, and environmental stewardship. Advanced systems thinking helps us address the complex interdependencies between economic, social, and ecological systems. By moving beyond linear approaches, we can recognize feedback loops, dynamic behaviors, and the interconnected nature of social and natural systems. In this chapter, we will explore the foundations and applications of advanced systems thinking for sustainability transitions. We begin with an introduction to advanced systems thinking, followed by an explanation of systems thinking and system dynamics. Next, we compare traditional approaches with systems thinking, highlighting the limitations of linear methods and the benefits of a systemic perspective. We will then delve into understanding system dynamics, focusing on feedback loops, interdependencies, and leverage points within systems. Practical applications in sustainability will be discussed, including case studies on renewable energy transitions, circular economy implementation, and climate resilience planning. The chapter also covers policy and decision-making frameworks, challenges and limitations of systems approaches, and how these methods can be integrated with the circular economy. Finally, we will discuss future directions and the importance of systems thinking for achieving the United Nations Sustainable Development Goals. This agenda will guide you through the essential concepts and practical tools needed for sustainable management. Advanced systems thinking is essential for sustainability transitions because it helps us understand the complex relationships between economic, social, and ecological systems. Linear approaches often oversimplify challenges, missing critical feedback loops and dynamic behaviors. Systems thinking, by contrast, recognizes the interconnected nature of social and natural systems. Key concepts include leverage points, system dynamics modeling, and the importance of planetary boundaries. Integrative thinking is emphasized, encouraging us to transcend disciplinary silos and foster holistic approaches. Case studies and applied examples demonstrate how systems thinking supports better policy making, corporate strategy, and stakeholder collaboration. By adopting a systemic perspective, we can design adaptive, resilient, and inclusive solutions that address sustainability challenges at multiple scales. This approach equips us to manage complexity and drive meaningful change in pursuit of long-term sustainability goals. Systems thinking examines complex economic, social, and ecological systems as dynamic, interconnected networks governed by underlying mechanisms. It provides a holistic view, emphasizing how different components interact and influence each other. System dynamics operationalizes this philosophy by offering tools to model these interactions, identify vulnerabilities, and uncover opportunities for positive change. The analytical framework focuses on feedback loops and temporal behavior, helping us understand how actions reverberate through ecosystems and organizations. A systemic sustainability perspective highlights the interdependence between organizations and the environment, acknowledging planetary boundaries and finite resources. By applying systems thinking and system dynamics, we can guide sustainable management, anticipate long-term impacts, and develop strategies that balance economic, environmental, and social objectives. This approach is crucial for addressing the complexity of sustainability challenges and fostering resilient solutions. Traditional linear approaches to sustainability often result in superficial fixes that fail to address the underlying dynamics of energy systems and environmental issues. These methods typically focus on isolated problems, missing the broader context and long-term consequences. Systems thinking, on the other hand, analyzes interdependencies among subsystems and understands long-term system behavior. It fosters holistic strategies for complex challenges, recognizing that environmental and social issues are deeply interconnected with natural, economic, and societal systems. Adopting a systems perspective is necessary for advancing sustainable solutions, as it transcends the limitations of linear approaches and enables us to design interventions that address root causes rather than symptoms. By embracing systems thinking, we can develop more effective, adaptive, and resilient strategies for sustainability management. System dynamics is a modeling and analysis framework that builds on systems thinking to study how complex systems behave over time. It emphasizes feedback mechanisms, delays, and interactions between components to explain patterns and predict outcomes. This approach is valuable for sustainability management because it reveals how decisions in one part of a system can impact interconnected subsystems, creating unintended consequences or opportunities for transformative change. By focusing on dynamic behavior rather than static snapshots, system dynamics enables decision makers to anticipate system-wide impacts and design adaptive strategies that balance economic, environmental, and social goals. Understanding system dynamics equips us to address root causes of sustainability challenges and develop solutions that are robust and flexible in the face of change. Feedback loops are central to system dynamics models and are critical for analyzing how systems evolve over time. In production and logistics, reverse and closed-loop supply chains often dominate system dynamics applications. These systems, driven by economic motives such as recovering financial value, can also contribute to sustainability by conserving resources, reducing pollution, and addressing social impacts. Circular economies and closed-loop supply chains require new strategies for sustainable management, emphasizing resource recovery and systemic resilience. System dynamics modeling helps balance economic, ecological, and social priorities by navigating the complexities of these systems. By understanding feedback loops, we can design interventions that reinforce positive outcomes and mitigate negative effects, supporting long-term sustainability goals. Sustainability requires recognizing the interdependencies between environmental, social, and economic subsystems. Traditional disciplinary silos often hinder holistic understanding, as researchers and policymakers focus on isolated variables rather than systemic connections. Metrics that treat sustainability as fixed thresholds may overlook dynamic challenges. Systems thinking advocates for process-oriented frameworks that focus on navigating pathways towards sustainability. Integrating both process-based and state-focused approaches enhances policy relevance and fosters adaptive, resilient, and equitable sustainability strategies. By acknowledging interdependencies, we can develop solutions that are responsive to changing conditions and capable of addressing complex, multi-dimensional challenges in sustainability management. Leverage points in complex systems are key areas where small interventions can trigger significant shifts in system behavior. System dynamics helps identify these critical junctures, enabling us to design effective interventions that amplify positive outcomes and mitigate unintended consequences. Understanding decision-making dynamics, such as the impact of policy goals, incentives, or penalties, reveals how changes in one part of a system can ripple through interconnected components. By targeting leverage points, we can create transformative change and address sustainability challenges more efficiently. System dynamics empowers us to pinpoint understudied components and design strategies that have a disproportionate impact, supporting the transition to more sustainable systems. Systems thinking and system dynamics are crucial for addressing sustainability challenges. They enhance policy design, improve decision-making, and facilitate systemic problem-solving, making them valuable tools in real-world applications. By modeling complex interactions and feedback loops, these approaches help create effective sustainability policies and inform decision-making processes. They enable us to address real-world challenges by targeting sustainability issues and utilizing systems thinking and system dynamics methodologies. Through practical applications, we can develop solutions that are adaptive, resilient, and capable of balancing economic, environmental, and social goals, supporting the achievement of long-term sustainability objectives. This section presents case studies that demonstrate the practical utility of systems thinking and system dynamics in sustainability management. By examining real-world examples, we can see how these approaches have been applied to address complex challenges in various contexts. Case studies highlight the effectiveness of systems thinking in supporting policy making, corporate strategy, and stakeholder collaboration. They illustrate how system dynamics modeling can reveal critical leverage points, inform decision-making, and foster adaptive, resilient solutions. Through these examples, we gain insights into best practices and lessons learned, helping us apply systems thinking and system dynamics to our own sustainability initiatives. System dynamics models have played a key role in Germany's energy transition by analyzing feedback loops between policy incentives and public adoption of solar and wind technologies. Subsidies for solar panels created a reinforcing loop, driving consumer demand and technological innovation while reducing reliance on fossil fuels. These models also highlight trade-offs, such as balancing decentralized energy production with grid stability. By understanding these dynamics, policymakers can design interventions that support the transition to renewable energy systems. System dynamics provides valuable insights into the long-term impacts of energy policies and helps identify strategies that promote sustainable energy production and consumption. H&M's adoption of a circular supply chain in the fashion industry highlights the utility of system dynamics. The company identified key leverage points, such as investments in recycling infrastructure and consumer incentives for garment returns. These interventions reduced waste and resource consumption, creating feedback loops for further participation. However, challenges like high recycling costs and fragmented supply chains require systemic coordination. System dynamics modeling helps companies understand the complexities of circular supply chains and design strategies that enhance sustainability. By targeting leverage points and fostering collaboration, organizations can create more efficient, resilient, and sustainable supply chains. Cities like Rotterdam use system dynamics models to address climate risks such as flooding. These models simulate interactions between urban infrastructure, ecosystem services, and community adaptation behaviors. Planners identified key leverage points, such as green infrastructure investments and flood-resistant housing policies, which mitigate immediate risks and build long-term resilience by reinforcing feedback loops between ecological health and human safety. System dynamics enables urban planners to design interventions that enhance climate resilience, support sustainable development, and protect communities from environmental hazards. By understanding these dynamics, cities can develop adaptive strategies that respond to changing conditions and promote long-term sustainability. System dynamics is crucial in designing policies that create feedback loops to enhance sustainability. For example, carbon pricing incentivizes low-carbon technologies, driving innovation and adoption. This creates a self-reinforcing loop that accelerates the transition to sustainable practices. Conversely, fossil fuel subsidies lock systems into unsustainable behaviors, creating degrading feedback loops. System dynamics models help policymakers map these dynamics and design interventions that shift systems towards sustainability. By understanding and leveraging feedback loops, we can amplify positive outcomes and support the achievement of long-term sustainability goals. System dynamics helps balance economic growth with ecosystem preservation by identifying leverage points and fostering collaboration. Tools like causal loop diagrams empower stakeholders to visualize interdependencies and clarify broader outcomes, such as reducing plastic pollution. Stakeholders include governments, businesses, and communities, all working together to build consensus around shared sustainability goals. Integrating policy design and trade-off analysis ensures that sustainability strategies are systemic and actionable. By reconciling competing priorities, we can develop solutions that harmonize productivity with biodiversity conservation and support long-term sustainability. Implementing system dynamics in sustainability management faces challenges such as integrating diverse data streams, stakeholder resistance, temporal and spatial scale mismatches, and risks of oversimplification. Fragmented or incomplete datasets can hinder analysis, while short-term economic interests may conflict with long-term sustainability goals. Political decision-making cycles often prioritize immediate gains, whereas sustainability outcomes require decades to materialize. Oversimplification risks omitting critical variables, leading to inaccuracies in predicting real-world outcomes. Interdisciplinary collaboration and adaptive modeling techniques are essential to enhance the effectiveness of system dynamics. Despite these challenges, systems thinking and system dynamics provide powerful tools for navigating complexity and developing resilient sustainability strategies. The transition to a circular economy represents a shift from linear production models to systems focused on resource efficiency and waste elimination. Systems thinking and system dynamics are crucial for understanding the interdependencies and feedback loops in circular systems. Integrating these approaches helps design resilient, closed-loop systems that balance economic, environmental, and social goals. Theoretical and practical synergies between systems approaches and the circular economy enable stakeholders to address challenges and explore future research directions. By adopting a circular economy mindset, organizations can create sustainable production models that support long-term resource management and environmental stewardship. Systems thinking highlights feedback loops in circular economies, where recycling reduces resource extraction and environmental impact. System dynamics models simulate these loops to identify leverage points for strategic interventions. Investments in recycling infrastructure and consumer incentives enhance circularity, creating self-reinforcing cycles. Coordination across sectors is crucial, as decisions in one area influence others. Holistic strategies and collaboration are needed to maximize the benefits of circular systems. By understanding feedback loops, organizations can design interventions that promote resource recovery, reduce waste, and support sustainable development. Systems thinking identifies leverage points for systemic change in the circular economy. Policy measures such as extended producer responsibility incentivize companies to design recyclable products. Technological innovations, like digital platforms for material flow traceability and sharing economies, support circularity. Behavioral nudges, including consumer education campaigns, promote repair, reuse, and rental models over disposable consumption. By targeting these leverage points, organizations can drive systemic change and enhance the effectiveness of circular economy strategies. Understanding and utilizing leverage points is essential for creating resilient, adaptive, and sustainable systems. Despite advancements, challenges in achieving circularity persist. Data fragmentation complicates tracking material flows across global supply chains, making it difficult to trace components across jurisdictions. Stakeholder coordination requires collaboration among competitors, governments, and communities, but industries often prioritize short-term profits. Behavioral and cultural shifts are critical, as consumer and corporate mindsets must move from ownership to circularity. Systemic nudges, such as tax incentives for repair services or extended warranty programs, can support these shifts. Overcoming these challenges requires holistic strategies, cross-sector collaboration, and adaptive approaches to circular economy implementation. To advance integration in circular systems, hybrid models combining system dynamics with digital technologies like blockchain and artificial intelligence are crucial. Equity must be prioritized to ensure circular systems benefit marginalized communities and avoid social inequities. Policy alignment, such as harmonizing the European Union's Circular Economy Action Plan with system dynamics insights, is essential for creating enabling frameworks. By embracing innovation, collaboration, and inclusivity, stakeholders can develop adaptive, resilient, and equitable circular systems that support long-term sustainability goals and address evolving global challenges. Thank you for your attention throughout this chapter. We have explored the foundations and applications of advanced systems thinking for sustainability transitions, examined practical case studies, and discussed future directions for integrating systems approaches with the circular economy. Your engagement with these concepts prepares you to contribute to sustainable management and the achievement of global sustainability goals. We look forward to welcoming you to the next chapter.